My name is Erwin Scholze, and I'm happy to present to you today Professor Hélène Seroussi, who will be speaking about a subject that you see titled on the board. Professor Seroussi probably does not need much introduction to at least some of you, but to the rest of you, probably she does. So let me just remind you a little bit about her background. Professor Seroussi graduated from one of the Grandes Écoles de Paris, the Grande École de Genève, the Grand Schools of Engineering in France, from the Engineering School in Paris, École Paris, I think in 2008, yeah? In mechanical engineering with honors, highest distinction possible. 3 years later, PhD, same program, same university, and then following her PhD, went to JPL, NASA, as a postdoctoral fellow for a couple of years, and subsequently joined the research staff as a research scientist for the next 8-9 years, during which she carried out the work that is very close to her heart, ice dynamics, in the shortest words, if you wish. That is the behavior of ice sheets in Antarctica and Greenland, and the effects of the ice sheets on ocean level. And we will hear more about that. Professor Seroussi has published many papers, over 100 papers in the peer-reviewed literature, and she's received numerous awards, and the most recent, just this past month, as Presidential Early Career Scientist in Science and in Engineering, which is a very distinguished award. So without further ado, Professor Seroussi is going to address us today on the future of ice sheets, combining observations and numerical modeling, and of course physics, to improve future projections. Let us welcome Professor.
Thank you very much, Erlen, for your kind words, and thank you all for joining today. Usually when you give a seminar, you know like a few people in the room. If you know 5, you feel like you're lucky. Today is pretty much the opposite. I feel like I see so many people I know, so many familiar faces, so really nice to talk to you about the work we're doing in the lab. And before starting, I just wanted to acknowledge all the people, grad students, undergrad students, postdocs that have been working with me over the past 3.5 years here. It's been a pleasure to work with them and really have constructive interaction, challenges, trying to answer their questions. And so, what do we work on in the lab? We work on, as Erlen was saying, ice dynamic and ice flow. So what does that mean? I studied the Greenland and Antarctic ice sheets. They are formed by the slow accumulation of snow that compacts under its own weight to form firn and ice, and then ice flows because of gravity. And so what we're seeing on this movie here is ice flowing. This is Jakobshavn Isbrae, the fastest glacier in West Greenland, and we see ice flowing from the, hopefully with the light, you can still see it, but flowing from the background towards us. And so ice is deforming, flowing because of gravity. And we see here ice calving. And calving is a very normal thing. When we talk about climate change, we always see pictures of ice calving, but calving is a natural process. Ice sheets are, it's like if in steady state, there is inflow from precipitation and losing mass from melting and calving. The problem happens when these two things are not in balance anymore. And I'll let you enjoy the rest of the movie. Pictures were taken every day or so over a 2-year period to see the evolution of this glacier. So as I was saying, we've seen that already. Yeah, okay. The problem starts to happen when there is an imbalance between the precipitation and the loss of ice, the output. And over the past 20 years or so, we've been able to measure such changes. And these movies here show the mass change for the Greenland and Antarctic ice sheet over a 20-year period, as observed by GRACE and GRACE follow-on satellites that measure local gravity. And from that, we can infer how much mass is lost. What we can see here, a few things here. First, on Greenland, we see the mass accelerating, going up to several meters of water equivalent over this 20-year period. And we see here Greenland is in yellow. We see these seasonal changes superimposed on a trend showing mass loss overall. And we also see that the changes are not uniform everywhere, with more mass loss in the south, along the coast, and these changes are propagating over time. Same for Antarctica, where we have some regions with very large mass loss, and others where we have some blue, so mass gain because of increased precipitation. Antarctica is very cold, so when climates get warmer, the atmosphere is warmer, can hold more moisture, and precipitation increase. And so we see that overall, Greenland has been losing about 269 gigatons per year, Antarctica 148 gigatons, and maybe gigatons is not your favorite unit if you don't work on this thing. So if you need a scale, this is, if you were to put 1 gigaton of ice, this is Central Park in New York, and so if you were to put that over all of Central Park, you would have a thickness of about more than 300 meters for each gigaton. And we're losing 269, 142 per year for these regions. And another order of magnitude you might want to think about is that 1 millimeter of sea level over the entire planet is 360 gigatons. Okay, so we know that these places are changing. Today, they've been changing over the last few decades. And we also know that they can change on much larger magnitude. We have observations of sea level from models and observations, proxy records showing the evolution of sea level over our planet over the past many million years. And mostly we want to look at what's happening over the past few 100,000, maybe a million year. And during this recent periods in the Pliocene and late Pleistocene, we had drastic changes in sea level. And during interglacial times, we had sea level that's been 10 to 30 meters higher than what we have today. And during the last interglacial, so here, about 120,000 years ago, sea level was higher, 6 to 9 meters higher than what we have today. And most of these changes are caused by changes in ice sheets. They can store massive amount of ice. Today is if all of Antarctica were to melt or we would increase sea level by 58 meters, 8 meters for the Greenland ice sheet. So these are massive amounts. And we know the Antarctica and Greenland can respond drastically to changes in CO2 concentrations and CO2 emissions. And so we can see here what Antarctica looks like during glacial periods, further extended compared to what we're observing today. And during interglacial times, large regions here in the West Antarctica can completely collapse. And so we know that we are observing changes today, and these changes can be massive and can happen relatively quickly. So what do we do in our lab? We try to simulate these changes, simulate how ice is flowing, how it's responding to climate change, and how it can evolve on periods, not such long periods, but on decades to centuries. And so we see here, this is my cartoonish view of Antarctica. We have the ice flowing. We have here grounding lines where ice is going from being grounded over the bedrock to floating over the ice. And a few things we work on first is looking at how the ice sheets evolve and how they contribute to sea level projections. And I'm going to start by talking about a little bit about that. We also look at a number of processes, and unfortunately there's no time to talk about everything, but a few things we think about is ice-ocean interactions, and I won't have time to talk about that today. We also think about basal conditions and basal processes, and to do that, we also use observations, and so I'll talk a bit about that. So let's start with predictions of future mass balance from the ice sheets. We've seen how the ice sheets are changing, and before going into what we do with models, I just wanted to do a bit of history here. So the IPCC is the Intergovernmental Panel for Climate Change, and they look at the impact of our warming climate on different components of the Earth system. And so in the 90s, the first assessment report and the second assessment report from the IPCC were produced, and they said that, well, they knew that there were changes on glacial and interglacial timescales, but at the time, we had very few direct observations, and the conclusion was that no major dynamic response of the ice sheet was expected during the 21st century, and sea level would come from thermal expansion of the oceans, either getting warmer, as well as melting of glaciers, so mountain glaciers, thinking about like the Alps, the Andes, and things like that. So we were safe. We knew everything, nothing to expect from the ice sheets. And then in the late 90s, 2000, we started to have more observations, and the picture started to change drastically. And we started to see that, well, they are actually effects of climate change, but the understanding of these effects, so like the rapid dynamic changes of the ice sheet, are too limited to assess their likelihood or provide even a best estimate of upper bounds on sea level. And so we went from we know everything to we know nothing. Things continued. That's not the end of the story. And so people started to work more and more on models, trying to use physical models for that. And then the following assessment, AR7 in 2013, concluded that projections of sea levels were larger than the previous report because of contribution from the ice sheets, but that significant uncertainties remained, particularly related to the magnitude of the ice sheet contribution. And I must notice that in these reports, there was no physical model used. It was all based on expert elicitation, extrapolating observation, empirical models, but no physics going on in these reports. So people continued to work on that. And finally, AR6 that was published a few years ago, finally we started to being able to include physical models because we had made enough progress on that. And the conclusions was that largest uncertainties in future sea level were still linked to the Greenland and Antarctic ice sheets with deep uncertainties in ice sheet processes and conditions around that. So still a lot of work to do. What does it mean that what is it that we're doing with these physical models and what's going into these IPCC reports? So this is, and why is this uncertainty so large? So here is this figure showing the global mean sea level change since 1900. And we can see here for different emission scenarios, so low emission all the way to high emission scenarios, the uncertainty in sea level and the different paths, and it can go anywhere from 0.5 meter to 1 meter. And then we also have for some of them the uncertainty associated with each scenario. And this uncertainty is what is mostly caused by ice sheets. And on top of that, we also have this dotted line, low likelihood, high impact storyline that is linked to possible instability processes that would cause drastic, very large changes on short period, but it's so uncertain that it's not even possible to include that in the overall results. So I kept talking about these models we're doing and physics models. What are those? So what I've developed with a few colleagues for the past 15 years or so is numerical models to simulate the dynamics of ice. So these models are just numerical models. We use finite elements, and so we have inputs in these models, geometry, topography, extent of ice, as well as initial conditions, boundary conditions, forcing, and the model calculates some outputs such as ice temperature, velocity, elevation, changes in elevation. And what goes in the models is something that many of you will be very familiar with, just your typical conservation laws with mass conservation. We consider ice to be incompressible, so we can calculate changes in its thickness evolution, conservation of energy. We have heat transfer. We can solve for that to get the ice temperature. And we have also stress balance. We consider that ice is an incompressible viscous fluid, and so we have Stokes flow to help us figure out what the velocity is. And so on top of that, we also have a bunch of parametrization for processes such as basal processes, calving, and so on. And then, going forward, we have observations, and we use these observations as input for our models. What's the geometry? How thick is the ice? And also to validate our models and compare the results with a number of observations. So that's what these models are. And when I think about Antarctica, that's how I see it. So this is a model showing the evolution of the Antarctic ice sheet. You have here the model velocity going from a few centimeters per year in the interior at the divide, all the way to several kilometers per year on these fast-flowing ice streams. And the black lines show the grounding line, so the boundary where it starts floating. It transitions from grounded to floating over the ocean. And we can see over this 300 period simulation, the ice accelerating, the grounding line retreating, and some of these large ice shelves completely collapsing. So this is one simulation that I've been running, one example, and we're working with something I've been working on recently was to look at. So this is one example of projections that goes into these IPCC reports, and these reports are based a lot more observations. And something I've been looking at is like how things extend beyond the 21st century, because we already in 2025, so 2100 is just around the corner. The results I showed for sea level was limited to 2100, and so we wanted to look at how things continue beyond that. And so we used results from 16 different modeling groups, using 6 different climate models that we use as boundary conditions to force and figure out how much the atmosphere is warming, how much the ocean is changing, and that resulted in 3 sets of simulation, 390 simulations, so a large data set of observations. And rather than putting the parameters of every model, which we would never have time to look at, these are the people doing that. That's a lot more interesting. All the people are working on that together. And so as I was doing these efforts, this is what we had seen so far for the 21st century, up to half a meter of sea level or so by the 21st century. And then when we extend that further in the future, we see that drastic change is starting to happen. And 2100 is actually kind of the turning point where things start to increase rapidly. And so each line here represents one simulation done by one ice model with one climate forcing. And we can see on the right here the spread of results. And the colors show each climate model that we're using as our forcing. And so the bars on the right show for each climate model the spread of results. And so we see that it varies and from 0 to 4 meters of sea level contribution. And we can then also look at the spread of results for each ice model that we're looking at. And so now looking at the different 16 or so ice models that we're using, the spread of results for each of the climate model that they're using. And we see that some models have a very small spread, and so they don't have such a response or less sensitivity to conditions, while others have a large sensitivity and result a lot bigger results. So we see all these ice mass loss up to 4 meters of sea level equivalent. Where is that coming from? What's happening? If we look at geographically where things are happening, this figure shows the thickness change in 21, 22, and 2300, so the average thickness change over the Antarctic ice sheet from all these simulations. So by 2100, we saw that there were limited changes, mostly thinning of the ice shelves, and then things start to increase drastically with massive thinning by 2200, and by 2300, we have almost all of West Antarctica impacted by such changes. And here in East Antarctica, we see some blue, so increased precipitation that can compensate to some extent to this mass loss, but not that much. And then the bottom row shows the standard deviation, and we can see here that we have we have some regions where the models are in pretty good agreement. There's a lot of thinning, rapid changes, but we have also other regions where there's a much larger uncertainty and increased standard deviation compared to that. So what's happening in these regions? Another thing we can look at is the position of these grounding lines, which is a really good indicator of how things are changing. And so we see here, so this figure shows the percentage, so it's a little complicated, the percentage of the ensemble that's going to be ungrounded at a given by 2100, 22, and 2300. So again, 2100, not so much is happening. And then by 2200, we start to see large grounding line retreat happening inland on both the Ross ice shelf and Roni-Filchner ice shelf in some regions. And that extends even more by 300 with several hundreds of kilometers of retreat for many models. And we see that in some regions, again, we have a really good agreement. All the ensemble members show the same retreat. While in some regions here, blue, for example, the Amundsen Sea region, there's a much wider spread and not such a good agreement. We can look at that in another way. Here, we're going to look at this retreat over these 3 lines here that I drew for Thwaites Glacier, the Saipol Coast here, and over the Bergenstock ice rise to see how that's changing. We're going to build this figure is a bit unusual way of looking at it, so we're going to build it step by step. So you have here the distance from the present-day grounding line. So today, what we're observing on Thwaites Glacier is that the grounding line is here. And what I'm showing here is the topography of the bedrock with the uncertainty. And we can look at for each model where the grounding line lines, then we're going to have the time on that axis, and we can look for each of these models at how the grounding line is evolving over time. So if you have a vertical line, that means the grounding line is not changing, it's just staying where it is. And if you had a perfectly horizontal line, that means it's retreating infinitely fast. And then so the slope kind of tells you the speed at which it's retreating. We have here just one model, and then we can add the other ones. And what do we see here? On Thwaites Glacier, we see that half of the models have their grounding line not changing much over time, like half of them are staying where it is, and the other half has large retreat. And what's really interesting here is that we see that the timing of the retreat is different. They all start retreating at different times. But then the slope at which you have this retreat is the same in all these models. And so what's happening here is that we have a bedrock that's going deeper and deeper and deeper inland. And so that means that the ice is thicker at the grounding line, and so when it discharges more ice, the flux is larger, it creates more ice, and as it retreats, it's going to flow faster and have a bigger flux, and you have a positive feedback. And so once you start having these effects happening, you have this large positive feedback, and the changes are driven mostly by the geometry of the ice, not so much by the conditions. Same thing for the other two places that I was talking about, but in that case, we see that all the models suggest large retreat in all cases. And when do we have that? Well, these two places are relatively stable today, so it's easy to produce something stable, while this one is already changing, and the models have a really hard time capturing such changes, which explains some of the difference. And so with all these models, we can look at the different sources of uncertainty. As I mentioned, we have a number of different ice flow models. We have a number of climate models. We also have something I'm happy to talk about more, but some of these ice shelves can collapse over time. And so we can do some multivariance analysis to look at how we have the total variance here of the entire ensemble using all these parameters. And then we can isolate the impact of these different parameters to look at the variations. And we see that the dominant one here is the blue one caused by the choice of ice model. We can also look at that to look at the percentage of this uncertainty caused by these different parameters. And we see here that the role of the climate that you're using, so different climate models that have slightly different climate conditions, increases over time over the 21st century to reach about 15% and then stays the same. The role of collapse, so these ice shelves collapsing, is really limited in the 21st century because you don't have conditions warm enough to cause liquid water and have them collapse. And then it increases rapidly after that. But the main thing that remains is that more than half of the uncertainty is caused by different ice models saying different things. So that's where we are today. There's a lot of work that we need to do to continue improving these models so that we can understand better this uncertainty, improve the models. And I just heard today, actually, what time is it? Literally 4 hours ago, that we had a grant funded by a private foundation to continue leading efforts for Antarctica over the next 4 years or so prepare for the next IPCC report. So lots of work to do, and we'll be ready to do that. So we have all this uncertainty. What can we do about it? How can we improve that? And how can we have better projections? And why, first of all, why do we have such problems? I told you that we've had lots of observations about the past decade or so. So we already looked at this mass loss. So this is looking at Antarctica. Again, we already looked at this mass loss, lots of mass loss from the Amundsen Sea region. We also have observations showing surface elevation and surface elevation changes. And we also have observations of surface velocity and velocity changes. But is there something that you notice when you look at all these observations that we have? All these quantities are all surface conditions. We're observing all of that from satellite data, and we're observing surface conditions, or in the case of mass, depth integrated quantity. So all the information we have is at the surface. We don't know much about what's happening below the surface. Englacial conditions, basal conditions. And that's one of the big problems that we have. So what can we do about that if we don't have direct observations? So, and why does that matter? Why are basal conditions so important? Well, basal conditions are going to control the sliding of ice. And so when you have, so ice is, there's two main things creating ice motion. The first one is englacial deformation. And so that happens everywhere. Let's imagine you have a bed that's frozen here. You have no sliding. You have just internal deformation. And then when the ice starts to be warm enough at the base to be at the melting point and to have thawed ice is going to start sliding over the bedrock. And that's what is creating these very fast ice streams. But we have no or very limited direct observations of that. So how can we constrain these basal conditions? Well, we have to use indirect methods. So that's work that Owen Seiner did as part of his undergrad thesis and that we just submitted. And we wanted to create the first map of Antarctic basal conditions globally. And so we combine different methods, synthesize of 2 methods, and then compare that with some direct or less direct observations. So what did we use for that? Well, first thing we can do is that we can use these models. We have all these models. They simulate, and I showed you like one of the things that goes in these models is heat conservation, and so we can look at the temperature at the base of the ice. This is using 9 different models, and we see that they have some agreement. West Antarctica is always warm, East Antarctica is colder, but there are some variations. And if we put them together, we come up with this model synthesis here, showing great agreement, so with the colors showing how many models simulate thawed or frozen bays at every point. And we see a good agreement with thawed conditions in West Antarctica, blue, so frozen bed on all the Transantarctic mountains that go all the way here, and then mixed, more complex conditions in East Antarctica with some regions where all the models agree it's frozen, others where they all agree it's thawed, but then the transition between these different parts varies in the models. And then, so that's the first method. The other thing we can do is that we have surface observations, and of velocity. We have velocity observations at the surface, and this velocity is the sum of both the basal sliding and the englacial deformation. And the so again, that's same as what we had before, the Antarctic velocity. And then this englacial velocity, we can estimate it based on some shallow ice models and these same equations I talked about. And so basically it's a function here of geometry, the ice thickness, the surface slope, as well as some parameters, E enhancement and ice hardness that depend on ice temperature and fabric and a few other things. And so we can calculate this deformation based on that, and then look at the ratio between the observed surface and the deformation. And if the ratio is more than 1, that means that the deformation cannot explain all the surface flow, and therefore you have sliding. And if it's less than 1, you can probably explain most of it with just englacial deformation. And so we run a bunch of, there are some uncertainties in these different parameters, enhancement, rheology, and so on. So we run a bunch of cases to look at the varying conditions. We see here the basal slip ratio is larger than 1 in many parts of West Antarctica, less than 1 in most of East Antarctica. And so we can create another map with the second method. And then we want to validate that. So the first thing we can use for validation is, I forgot to mention that, here we have a few deep ice core that drilled all the way to the bed and can directly observe if the ice is thawed or frozen at the bed. That's these dots here, with black circles. The second thing we can do is that we have observations of surface elevation. And when we look at these surface elevation, there are places where we see that there are rapid, very localized changes in surface conditions, and with just very small places, a few square kilometers, where the elevation drops very rapidly. And these are caused by subglacial lakes that drain. And so we can know that we have lakes by looking at that. Some people have been coming together with catalogs of these lakes. So these red lakes here are active lakes where you have subglacial lakes draining. And then we also have ground penetrating data that shows where we have, and you're looking at the reflection, we can see where you have bright reflection that suggests that there is the presence of liquid water at the base. And so we can use that to figure out where we have also lake, but these ones we're not sure how much water there is. So we could consider that these are stable and not creating so much water. And then these active lakes, because they have so much water, they can drain, and we can even see that at the surface. We can look at where the water is flowing using some simple routing models we have here based on the hydraulic potential, and so we have here the elevation at the base, and then because there is ice above that, that's also the second component of the hydraulic potentials, which allows the ice to go up terrain if the ice change in ice thickness changes and decreases rapidly. And so these channels here are these routing paths where the active lakes can drain. And so we can put all this together to look at basal conditions. And so this is the first map looking at the synthesis of basal conditions for Antarctica. We have the background shows our 2 methods showing where it's likely, the ice is likely to be thawed at the bed, where it's likely to be frozen in blue, and then these uncertain regions. And then we can put our validation on top of that. So the circles with black contours, frozen or thawed, which have a good agreement with our synthesis, as well as all these hydrologic paths, which you can see are really in areas where both methods agree that the bed is thawed. So that's validation of these results. And so that's the first map showing a kind of synthesis of Antarctic basal conditions that we, as I said, we just submitted. And so we can use these observations to try to get at these basal properties that we can't measure directly. But can we capture the recent evolution of ice sheets? And so again, here we're going to look at mass change. And so we have on top Antarctica, and then on the bottom we have the Greenland ice sheets. And we have here all these lines similar to what I've showed before, all these models and how they simulated mass change from 2000 to 2025. And then in blue, we have these observations that I talked about with their uncertainty. And we can see that very few models are able to capture these changes. And especially for Greenland, all the models simulate less change than what we observe. And so probably means that our predictions are underestimated. Can we do something better than that? So what can we do? So as we have these observations, can we test things? Can we test things better? So here now I talked a lot about Antarctica. Now let's move to Greenland. So here we're going to look at what we can learn about basal conditions with these changes over time. And so we have here this region in northwest Greenland where there are 10 or so glaciers. And this is work from Youngmin Choi, who was a postdoc with me. And so we have this region, we're showing here the ice flow. And we, as I said, we're starting to have more and more observations, and we can see how the ice was changing over time. And so on the right here, we see how the velocity changed over a 10-year period, with most regions accelerating and flowing faster. What do we want to learn? Well, as I said, we use basal physical principles, and then we have other things we need to include in the model, like basal sliding. And basal sliding, because we have few observations, there's no universal law. And so there are maybe many different sliding laws that have been proposed over time. Here, tau b is the basal stress, and it's mostly a function of basal sliding. But you also have some that include effective pressure, and here, and lots of variation thereof. All these things have been published in the literature based on lab experiment, physical principles, and so on. So, but we don't know what works where. Can we say something by using these observations? And so here, showing for one, so just taking one of these glaciers, we're looking at we can compare all these different sliding laws and see how they can reproduce the changes or not. So let me zoom on that because it's a little small. And so here for two of these sliding laws, Wertmann and Bud. Wertmann is usually used for hard bed. Bud sliding law includes effective pressure, so you have a bit more feedback when the ice changes. We see here in the dotted lines show observations of velocity over at different times for one of these glaciers. And then the solid lines show the models, and so the models are all initialized with the same conditions matching observations in 2008, 2007, and then we let it run with the different sliding laws. And another thing you might have noticed is that we also don't know the exponents for these sliding laws. So higher exponents will create more plastic deformation, lower one more viscous. And so we initialize all our models in the same condition and can test how different sliding laws and different exponents can capture such changes. We've done that for all these glaciers, and the conclusion overall was that ice was more plastic than is typically used in models, and that sliding laws that have effective pressure and capture that kind of feedback match better the observations. And so we're doing that based on velocity observations, but then we can see, we also have, as I said, observation of mass loss, and we can see when we do that, how that matches or not these independent observations. And so we have here the mass loss for different sliding laws and for different exponents, and we see that the ones that had a better match with velocity observations also match better these independent observations of mass loss, suggesting that we indeed capture the right dynamics here. And then, does that matter? What's the impact? Well, the impact here we're looking at the mass loss from these different glaciers in that region. And typically, ice models would use sliding laws with low exponents, typically m equals 1 or 3. But then these results suggest that the bed is more plastic than we thought. And when we do that, we see that the sea level contribution by the end of the century from these glaciers is increased by 1/3 to 1/2. And so more contribution. So we see with that we can try to understand what kind of, what does the basal sliding looks like. But can we do even better than that? And so there's something I just put under the rug, and maybe some of you noticed. I said as we initialize all our models to match the conditions in 2007, and then we'll let it run. How do we even do that? So if we knew the basal friction, this is just any random glacier, if you knew the basal friction, we can simulate the speed of the ice. We have the basal stress, and we can simulate the well. But we don't know that. What we know is what we have at the surface. We know surface observations. So from that, can we infer what are the basal properties? And alpha here is any coefficient that we had in your favorite basal sliding law. So to do that, we can, but it's an inverse problem, a little harder than the direct problem. And so how does it work? Well, we want to, what do we want to do? We want to have our model match our observations. So we have here Vx, Vy, our model velocity, and then Vx ups and Vy ups, our observations. And we want to minimize the distance between our model and our observations. And here we have regularization term. Happy to talk about it if you want. And we know that the ice has to follow these stress balance equations, as well as the rheology that we use and these basal conditions. And so we want to figure out what these friction coefficients are, how they vary over space. To do that, you have your cost function. You can calculate the gradient of these cost functions with respect to the parameters you're interested in. For example, here, alpha. And then, so that gives you the direction where you should go, and in that direction, find the minimum value. And so this is a nonlinear process. You have to iterate. You start from your initial guess. Here, this part here is dark blue. It's 0 because it's floating, so there's no basal friction. And then you start with a constant guess value of 40 or something. With that value, that's your model velocity. And then you have your observations, and then you can calculate the cost function with that, look at the gradient, and improve. And you have slightly, after one iteration, you start to slightly better reproduce that model velocity, so have this faster flow here, and you start to see some pattern in the basal friction. Then you continue iterating, and have after a few more iterations, you can improve that, and you continue on until you match your observations. And so that's what we use to initialize the models. The problem, so, and this is great, but as we've seen with some, and so, yeah, that same thing, our optimization problem, and that's what we're doing, and as I said, we initialize that. Let's imagine that this curve is just like for 1 point on the ice. We match our initial condition here, and then we initialize our model like that, and we let it run, and we hope that, well, if we have the right conditions, it will more or less follow the truth, which is our velocity and thickness change, and follow that. But in reality, it looks more like that. It can grow faster. It's not very good because we have all these other uncertainty. But now, if we have more observations over time, we can start to have more observations. So can we add that into our optimization problem? Well, yes, we can change our cost function to include, to sum the difference at different time steps. The problem here is that so far we could look at our stress balance equation and calculate the gradient by hand. It's not easy, it's not funny, but you can do it by hand. The problem is now here we start to include all our other equations and parameters that change over time. The temperature, the grounding line position, the front position, the thickness, and so on. And so now it's completely intractable to do it by hand. So for that, now we have to use algorithmic differentiation, and with the help of some colleagues who developed CODIPAC, I'm smiling because Max, who develops that, is visiting us these days, and he's in the room, so thanks for your help. We can constrain the model over all these periods using more observations. And now by capturing the trend, hopefully you're on the right trend, and you can continue better. So does that work? We did that for Keir Glacier in West Greenland, so this one glacier here. We have here the velocity of the glacier, and that glacier has been changing over the past 30 years or so in response to its ice front retreating. And we chose this glacier because it has great observations. We have velocity data back from 1985. And so we initialize our model with that, over that period, 1985 to 2007, infer friction and rheology parameters, and then look at what happens when we let the model run freely after that. And so these are the two options. The first one is the snapshot calibration with just one period, as I was showing before. Or we can do a simulation over this entire period here, over 20, 30 years, 20-something years. And so all these triangles show velocity on this flow line here for these different points. And then the dashed line shows the model matching these observations. We tuned the model to match that, so it's doing what it's supposed to do. And we also have, again, independent observation of mass loss showing how that's changing over time, and the model and the observations are pretty much spot on, so we can capture that mass loss. What's happened when you do that over the next 10 years? Does that work? Does it help us predict things better? Well, we can see here when we have snapshot inversions, the glacier accelerated quite a lot, but the model cannot capture such a rapid acceleration. While when we calibrate it with the transient assimilation, we see that it continues to be pretty much spot on. So by doing that, we are able to improve these short-term predictions. And what is remarkable here is that you see that during this transient calibration period, there were relatively limited changes. The glacier was not changing that much. We calibrated it over that relatively stable period, and still when it started changing, we were able to capture these rapid changes. And when we look at the mass loss, we see that the snapshot inversion underestimated mass loss, while the other one is pretty much within the uncertainty of the mass change. So we can do that. We have 25 years of data, but that's not always the case. This is like kind of the exception, not the rule. So can we do it over shorter periods? We did that over 10, 15, 5-year periods. And in summary, it doesn't matter. As long as you have like a few, even like 5 or 10 years, where you have all these observations, you can capture the changes better, you can calibrate and initialize your model better, the initial conditions are much better, and you can capture the changes. So that's great. Problem is that a Kjær glacier is this domain here, like in black here, and you barely see it, that's normal. It's one out of more than 200 glaciers in Greenland. And so how do we go from that to being able to do large-scale simulations? So that's things we're starting to work on. That's something that Jessica Badgley, another postdoc, has been working on. And so extending that we want to do two things. We want to extend that to larger regions. And so she's working on this northwest region of Greenland here. And we want to see if we can do better than that. We used annual changes, but we saw at the beginning that Greenland has lots of seasonal changes as well. So can we even capture better than these annual trends? And so for that, we limited to more recent observations if we want to have these seasonal changes. So we're looking at the period from 2007 to 2022. So we have this model, continues to have very high resolution, 400 meters at the front, so we can really capture all these narrow outlet glaciers in Greenland well. And this is what it looks like. So same as what we had before, we have in gray observations of mass changes. And now we see we have these better observations showing seasonal trends in mass change. And first we have this model with the snapshot inversion. So we just use initialize in 2007 and let it go. Can we capture these changes better? Well, we have observations for that, and so when we do transient estimation, we are able to capture and stay within the uncertainty of our observations. And so by doing that, we have 12% more sea level with the transient assimilation. And if we want to circle things back to where we started with these global projections, all these blue lines here show these global ice models at continental scale extracted over that region. And you see that these regional projections calibrated well match the observations so much better. And what's the impact? Well, if you look at the impact on projections, these were all the projections over the 21st century, and our new projections for that region are much higher than that, more than 5 millimeters, even when doing just regional models, and another 5 millimeters when you do transient estimation. So the impact is big. And finally, so we have these two methods, and here all of these is using high emission scenarios. We can also compare the role of initial conditions to the different emission scenarios that we're going to head towards. And so we have here in purple and yellow the same curves, and then these dashed lines show low emission scenarios. And we see that between now and the middle of the century and until about 2050, the calibration method and the initialization method that you use has more impact than the emission scenarios on sea level. And around the middle of the century, that's where both start to be equal, and then the emission scenario starts to dominate. But even then, it can represent 10 to 15% of sea level projection, so not something negligible. I'm going to stop there. And so in conclusions, we talked about large-scale projections and how Antarctica is susceptible to large changes. After 2100, there are large uncertainties and consistent retreat when these instabilities starts kicking in. One of my colleagues said, published in the paper a few years ago, that numerical modeling of Antarctic ice sheet has gone through a paradigm shift over the last decade. I think the next decade is going to have an even more bigger paradigm shift. We've had a revolution in the number of quality of remote sensing observations that we can use, and now this revolution has to translate into models being able to use that. And so integrating new observations at large scale, and also that opens all these new doors to look at seasonal changes and seasonal processes. All this work is obviously collaborative efforts, talking to people to go from algorithmic differentiation, climate modelers, and so on. And I've been able to work with all these diverse team. And then I think no ice or glacier talk is complete without showing a nice picture of the ice on a bright, beautiful sunny day. So here you have it, a picture of a nice sunny day on the Greenland ice sheet. Same place that we looked at the movie at the beginning. So you have it. Thank you.